запускаем. Ее Шанель.
Во. Чувствую себя завхозом.
А это разница, по-моему, никакой, тебе не кажется? Что завхозами и тем, что ты делаешь.
Ну, вообще, да.
Okay, so hello everybody. Today we will be talking about parallel algorithms. This time I will try to do this course in English. I hope this will be not very bad at the end. Okay, so let me try. I have a plan somewhere on my laptop to teach. I already looked my lecture from the previous year, so I approximately know what I'm going to talk about. What I don't know is whether I have like 1.5 hour of lecture. That's a very interesting question, but like let's start then. I will start from what the parallel programming really is and what is the differences with concurrency. Okay, one moment. I will look on my video to open their chat there because the people are watching online. Can I do that, please? YouTube, please allow me. Oh, there is no internet for me. Okay, that's reasonable. Yeah, there are so many problems today. It seems that there is no Wi-Fi connection here, right?
I think yeah.
Okay, that's pretty cool. ITMO guests?
There is no routers here for Wi-Fi.
Yeah, but
For ITMO guests, it seems it's here.
Well, ok.
That's
I'm writing you with it.
so you're not the groundkeeper then, since you don't know all the details. Where's like, okay, we had the Wi-Fi router somewhere there at the top, but like, I don't see. Why? Okay. It seems I cannot properly write шахматные too. Because I have like this without Russian language, okay? So
Maybe I can help.
I don't know, like in other place I did this like from the let me hope that I wrote it right now correctly. No. You sent it. Okay. Good. If okay, no, I wrote it pretty right from the second time. And there is no internet, right? I cannot open YouTube in that. Okay, yeah, I will open this on the telephone. Then, sorry guys. Okay, yeah, I have a chat here, so. Okay, yeah, so like there are 5 people who are watching it right now, so you are 5 also, so you're outreach the people. So like I will talk about parallel algorithms during this course. So what is the real difference between parallel algorithms and concurrent algorithms? It's quite simple, is that the parallel algorithms, or what you were thinking, this is exactly as standard algorithms. Like if you know algorithms and data structures, you're pretty sure to know what algorithm is. So there is an input, there is output, and there is something inside. You give it input and you get output, like a black box. In the sequential algorithm, there are no problems because here you just execute everything sequentially and you don't care about anything. With a parallelism, it's a little bit more complicated because you are given input and you are starting from the sequential start. So you are starting from the sequential and you add end in the sequential. So typically you create here, you have the starting synchronization point of all their processors. So you can like fork and join like and then at the end you just merge this everything together and you have an output here. With their concurrent algorithms, it's a little bit more complicated. So like if someone wants to change their course on concurrent algorithms, we have this going in 3rd year of bachelor's, and it started right now. I mean, this is not, this remark is not for their bachelor students, but for masters. If you want to know what concurrent programming is, then you can talk with me about changing some subject to that one. So, and for the concurrent algorithm, that's a little bit more interesting. So you have P processors that are not synchronized. So you have P processors, and each processor has its own input. Okay, and so on. Okay, so like it's input here, and there is a data structure. So what the concurrent algorithms typically doing? There are several processors who are trying to change the data structure that is going on there. So, for example, for concurrent data structure, typically it is set data structures or like databases data structure indices. So you want to have like insertion, removal, and contains, and possibly some other like range queries where you want to know like the range of the elements. So in databases it is pretty everywhere. So you have here input and you have here your data structure that is changed outside. And here you have everything synchronized to the top. So you can use this, like this knowledge is very large, that you can see like that everything is synchronized at the beginning. While here you have their random accesses kind of, so like there are paths in there, and like some of the processors can try to change the same cell at the same time. So you have to, and you have an output for in comparison to there, you have output for different processor, separate output, because like each input is the separate operation, and you want in the output the answer for that operation. And kinda you don't have the information that everything on the top is synchronized. So kind of you have to think about the synchronization of everything inside this black box. So that is why concurrent algorithms are much more complicated, because you have to consider all their problems of the synchronization. But this is not their case in our lectures, in our subjects. So we are going to talk about the parallel algorithms where kind of the synchronization is inherited by the model. Now I will go a little bit into their history on how parallel algorithms evolved. Yeah.
People in YouTube,
In YouTube?
tell you to mute Telegram because they hear notifications from it.
Oh, okay, sorry. I don't hear them. Somewhere here. Okay, now it should be. Thanks, Alexandra. I hope there are no more notifications right now. I don't know why I cannot hear it, possibly because it doesn't have. Okay, so we are working on that model, and let's come for the history. So today will be today's lecture will be only the introduction. So we cover kind of history and the similar stuff, while from the next and the models. While from the next we are going to talk about algorithms itself. So we start with the PRAM. So everybody knows what RAM is? Okay. It's a little bit different. It's random access machine. So it's not memory, it is machine. PRAM means the parallel random access machine. So you allow to go to memory concurrently, like at the same time. How the PRAM typically works? So for like in the 70s, when there will be no idea about how the concurrency or multiprocessor will ever work, they thought that they had a pretty nice idea that all the steps are synchronized in this model. So you have the step 1, and you have n processors there, and each make their first step as one kind of large operation. Then you have the synchronization barrier that is inherited by the model. So here is 2. Synchronization barrier 3. And so on, and the last one. Okay, I will remove it here. So each program is given for the separate processor, like one program per processor. So like there is the program first, second, third, and n. I think you know the problem, why it doesn't work in the real computers. Do you have any idea?
Expensive.
Yeah, it's really expensive to synchronize everything here, right? That is why this model hasn't lived for a long time. I mean, it lived from 70s to zeros, like to 2000, but then the concurrent and parallel algorithms understood that this is not the really good model. I will explain you why this model is not very good either. What is this one step? We consider that this one step is either read x, write to x, y, and do some arithmetic operation. And by that, we have 3 different PRAMs there. Do you have any idea what is the difference between these PRAMs? Could you guess?
reads
Yeah.
and writes.
Yeah, exactly. Exactly. This is parallel read and write. So there is EREU, which is exclusive reads, exclusive writes. Then CREW, this is concurrent reads, exclusive writes. And CRCW, concurrent reads and concurrent writes. So what does it mean? This means that at each moment of time, nobody can, like only one processor can either read or either write. So this. Then concurrent read, exclusive write means that we can make concurrent reads from the same cell at the same time, or either only one processor has write on that cell. Concurrent read, concurrent write is the most powerful of these models. So it can do concurrent reads and concurrent writes. So this model is a little bit more complicated than the previous ones because of concurrent writes. We have to define the behavior of the writes, because like if several processors writes at the same cell, they should decide who will be the winner kind of the write. And there were created a lot of different models like that. The most kind of not useful. The most usual ones is common. Common CRCW means that you can write at the same time only one value. So all it is allowed for all processors to write the same value. If it is not, then it is not. This algorithm is not in that model. So you can write one, and so on. So then priority. This means that the processor with the smallest identifier wins. And there is random. Random is pretty simple. It means that someone has wrote it. Nobody cares who, but someone has wrote it. Okay. Yeah.
Is it guaranteed that in a random model we'll write one of values?
Yes, yes. It is not the kind of real world model again. I mean, if we're talking about the very small parts like ints or so, then it will work because like the cache lines are atomically flushed. So I mean, until you're not going out of the cache, everything will be fine, even on the modern PC. Okay. Yeah. So like right now, I want to talk that this algorithm, these models, kind of you can prove that they're equivalent. So in the sense that they are not really equivalent, but they a little bit equivalent. So like that is, I have to tell you what is the time. So there is work time framework. Work, it is how much operations you've done in this algorithm. Time, it is how many steps there are. So in this case, it is pretty simple. Like the time here is k, and work is n times k. So there is nothing really interested here. Why I'm telling you about like the time and work, it is because you can emulate any CRCV on exclusive read, exclusive write with additional time times log n. So I mean, they're kind of equivalent, but not really. Like these three are definitely equivalent, so they can be get from one to another in constant time additional. But like, if you want to get from CRCV to EREU, then you have to pay logarithmic penalty for the time. Their idea is pretty simple, so I will give you like brief explanation why does it work. Because when you want to get this CRCV from EREU, you could say that like let us each location be like, so there is memory location M, and it is split into n parts. And since you have exclusive read, exclusive write, to come up with the write, you just go to the corresponding cell and you update it. Then when everything stops, you have to aggregate all the information there and choose like who wins this operation. And then you can finally understand what is the real value of them. So, and because you can do this kind of in divide and conquer manner, so you can go like you want to find their okay, like there is nothing really interesting there. With priority, you just have to find the first element that is not empty, kind of, and then you just go like this binary. Okay, this is empty, then and this is empty, then this is empty. It is empty here, but not here. Then the value comes here, and so on, and then you will get the real value at the end. So this height of this execution will be logarithm n, because like it's binary splitting, and that is why you get the time like it. As you can see in the work manner, nothing has changed because like each operation made the same amount of operations, but the time is changing. Okay, yeah.
What if some thread doesn't have work to work?
Yeah. Yes, this is possible. You can have their empty.
Like
No operation. Yeah. So like this, I will write right now the program that is similar to what was going on with PRAM. So that is why the work is just n times k. So there is nothing pretty simple or nothing pretty hard doing here. So we kind of think that this are skips. Okay, let me. I have written to myself a code, so I will not make a mistake there. So right now we will understand how to write the sum of all the elements. You are given an array and you have to find the sum of all the elements of this array, and we're going to do this in prom. So you like we start with a separate program for each processor. So it starts with ID. So with ID, we know the ID of the processor. So we will work with that later. Well, it is a little bit more complicated because we have each atomic each simple operation to be written down. So for example, if you want to sum the elements and write it, it is 4 operations. It is read the first argument, read the second argument, sum them, and write it. That is why, because each primitive operation is split here into them. So we read ID, then you write the ID A, then I go for H1 to log n, the process is less than and equal to n divided by h. So we do read b by d minus 1 x. I think we will go in notation with 1, so it's not with 0. The array is not from 0, everything is from 1, so that is why we need to like this, and then we z equals x plus y, and write dIdz. So, and else we do skip 4.
Or it's like skip for operations.
Yeah, it's like 4 operations here. So like here we have 4 operations. Like if we're successful, then we have 4 operations. Otherwise, we just skip these 4 operations somewhere.
Is n like a number of threads?
Yes, and
constant?
no. Okay, so here we consider that the number of threads is the same as the number of elements.
I mean, we know this number before starting.
Yeah, we know this number. Yeah. So we are starting like how does it work? So like if you. So here is the trickiest part of their PRAM model. Is that kind of if it wasn't synchronized, then you will have a huge problem because you will read 2 elements and write it back, and if it is not synchronized, then we can get the chaos everywhere. I mean, one processor can write before someone reads, and we will get the incorrect behavior. While right here, everything is fine because you at first read, like all the processes read it, then all the processes read it again, and then they sum up and write it back. So you have this array B, then you are doing the following. You take the sum, like your array kind of shrinks 2 times. So you sum each element here. Then you're going again sum the here, and then you finally sum to 1 cell, which is the answer. So there is nothing really complicated here. You just have this logarithm layers of trying to get only the prefix summed up. Okay? I hope okay. Yeah. Possibly I should use the chat. I don't know whether there are questions in the chat because I don't see it. Okay. What is the time of this algorithm? Yeah, log n. There is nothing hard here. So, and the work will be then n logarithm n. Okay? There is the problem, obviously, that it seems that we use processors inefficiently because the work is n logarithm n this time, and really their computation of the sum can be done in linear time, right? So this means that we have to update our model a little bit so that the total work that is given is not written as number of processors multiplied by the time of the algorithm. For that, there comes another model, which is the model with parallel for. Instead of having for here and like identifier per each processor, we just implement it in the way of P4. So we have, we have for, because we have logarithm height of the computation. And then what we're doing, we are going not by if identifier, but P4, I from 1 to n divided to h. And do the same, like read e to id minus 1, x, and so on, like everything, the rest is the same. So instead of forcing each processor to operate each time, like when you have n processors, instead you kind of emulate this on any number of processors. So if you have like 2 processors, you can emulate this parallel for. Like you just go, like how your parallel for looks like. It is the first, second, and like n divided by 2 times h, right? And there is operation. So what how we schedule this? We will schedule this like from left and down. So we'll sketch like that and then in that direction. And right now we don't care exactly that we have n processors at the same time, right? So because like if we have 2 processors in total, we can evaluate this 2, then this 2, then this 2, and so on. So kind of this model allows you to alleviate an issue, to evade an issue with their fixed number of processors. And because of that, right now we have not the work and time, right now we have work and depth. Where depth is, suppose we have their infinite number of processors, what will be their running time? So all this force, or parallel force, will be like one execution. So there will be like, at each moment you will like compute the whole line, whole first operations, second operations, third operations, and so on. Yeah.
Am I right that in previous code we have splitting our jobs just at the start? And
Yeah.
But here we splitting our jobs only when we get to parallel for.
Yes. Yeah, and this is exactly why the depth here is logarithm n, right? But the work is already not n times logarithm n. It is linear.
We count work, supposing we have infinite number of threads.
Yeah. No. The depth is infinite number of threads. The work is when you have one processor. Okay, so like this is the total number of computations we did in total.
Then I have a question.
Yeah, sure.
So we are now splitting our work into separate parts.
Mm-hmm.
Then giving these parts to the threads we have.
Yeah.
And what if we have such unlucky number of threads that one of the jobs depend on the previous that we scheduled right now?
I mean, here is not this problem. I think doesn't arise here because you just make parallel for there. You don't have anything else. You just have parallel for, and even possibly like in their starting model they didn't have nested parallel fors. So like that's the pretty. This is simpler model in some sense. You don't have to care about any dependencies because you kind of you create this task, yes. So kind of here this could be considered as in fork join you have fork in 2 processors, while here you have the fork in like all the processors. But this is like these algorithms are, I mean, they're simply hierarchical. So you have only nested parallel fors, and with them, like you cannot reach for the memory that was in some other branch. Okay. Let me check if I'm doing everything fine. To be honest, I have no idea whether I'm doing this. Okay. Yeah, so summation as an example, we did it. We have to come up with, okay, there is nothing in the chat. I mean, they're looking right now 2 persons. I'm pretty popular out there in the internet. Okay, you've seen that this is kind of not what we really want, because it is really complicated to come up with parallel fors, and that kind of you have. I mean, it is quite simple in some sense if the program is pretty simple, but if the program becomes complicated, you cannot work with p-force anymore. Like this is not enough for you. And for that, their works fun model was created. Like, as you can see, the work never changes, but the name for the second term always was going to change. So like it's time, depth, and span. So this time, you're given a little bit more interesting object, which is a little bit more interesting than parallel fors, as the directed acyclic graph. So you have your program written as DAG. For example, the parallel for, like the parallel for 1 to n will be like kind of like this. Like you have n children. But I'm going to talk, like it is sometimes possible you can have like n parallel operations created, but you can understand that if you have n is pretty critical, pretty large, then you will have to span a lot of threads. That is not exactly what you really want, because that will slow down the computation a lot. Instead of that, we allow only simple operations for fork and join. I'm pretty sure that someone of you know that from their concurrency course, where we have fork join pool. I know, like, did Roman discuss that? I have no idea. So like this is pretty simple. So again, you have this synchronization point at the top, which we were discussing in the very beginning. So you have the synchronization point, and then you could spawn 2 threads, and that's it. So this is fork, and this is 2. So we have their execution, then you have again fork, then you have, I don't know, like no fork, but I don't know, like graph like that. Okay, this is your computation. This is for each primitive operation. Rather than you call fork, then you create two processes in parallel, or you do nothing and you just make your operation here. for example, here it's happening join, so you join these two threads back again, and then you go sequentially, and then you go to the end where you have join again. Okay. You can have more fork on 3 threads or on 4, this doesn't matter, but typically it is leaving as the fork onto 2 processes. I mean, there are not really the processes. Like I will give you a glance for a future a little bit. We create lightweight threads. So in Java or in some other language, when you have threads, you pin your thread to the core. So if you have P processor, P cores, then you will have P threads. There is nothing really. Or either you give this for the scheduler, but like let's not talk about that. Suppose our processor has only P cores. What I was talking about.
That we have
Lightweight threads, yeah. So the tricky idea is that you not always have the infinite number of processors. You always have like smaller number of processors. So for example, if you have 3 number of processors, you can't have these 3 threads living at the same time because you have only 2 cores. You cannot have more. That is why each of these tasks like each fork creates the lightweight threads. It is like coroutines in Kotlin. So these are lightweight threads that are much cheaper. So they store only stack, and that's it. They store the stack and where they are in the program. Yeah.
Does that mean that we don't have synchronization by levels as in VRAM?
Yes. This can like the evaluation here can be like the first process like already finished this 3, but this one only starts. So it is possible. It's possible to do that, of course. Yeah, so there are lightweight threads, and that is why the creation of the lightweight threads, let it be lightweight threads, are much cheaper than creating their hardware threads on their own. Okay, what about the model then again? So you have the computation, which is given to you in the form of the directed acyclic graph. What are the complexities of the algorithm? The work is the number of these circles. So this is the total number of work in the algorithm, kind of on one process or one core, like that. And the span is again like number infinite cores. So you kind of do not care about the number of processors in the machine. You want kind of to understand how your algorithm approximately works on any machine. So like that is why you come up with this span approach. So for example, here the work will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, while the span will be 1, 2, 3, 4, 5. Because here is also 1, 2, 3, 4, 5, 6. Yeah, so it is 6. So yeah, okay, yeah. Then the span here is 6, because like this is the longest path, kind of. Okay, yeah.
Why we have to have 2 different complexity functions instead of having one with parameter of number of cores?
Yeah, yeah. I already answered this question like 1 minute ago. We don't care really about how it works for the specific machine. We care about how it in generally works. I mean, in any like yeah. Let me go a little bit deeper. I mean, if you have P, the number of processors, everything will be much more complicated to calculate. Because it should depend on the parameter P.
So it seems like we just want to know the worst case and the best case.
Yeah, and then I will explain right now how to Yeah, how to get their approximate running time on P-processors. When you have P-processors, you can predict approximately how it will work. I mean, by that you can think that we can get from work and span their running time on P-processors. Not exact, but similar. Okay. So about the scheduling, you have separate ways of scheduling the directed acyclic graph. There are two ways. There can happen online scheduling and offline scheduling. Offline scheduling is when you're given their DAG in advance. So you're given this DAG and you want to schedule how to, in which order you want to compute each of the nodes. While in online scheduling problem is much harder because this directed acyclic graph appears not at the beginning, but you explore it. So I don't know, like you could have like these nodes that are explored at the same time, and you cannot see anything here. So you see only the next the vertices that are ready. So this was already computed, and you see only two nodes, and you have no idea what's going on there. So this is online scheduling. Okay. What I was talking right now is that we will start with offline scheduling for a moment. So we're given a directed acyclic graph, and there is a pretty simple theorem which is named Brandt's theorem, that handover level by level scheduler works in W divided by P plus S, where W is work and S is span. And P is the number of threads, yeah. So it says, if we have level by level scheduler, then the running time of the program will be not worse than that. The proof is pretty simple. So let us beat it level by level. For example, by their depth from the root. By the depth from the root. So you have like this work 2, this work 3, and etc. Okay, if we have level by level scheduler, what will be the computation time of the first level? 1. Not exactly this. I mean we have W1 on the level, so it is not 1. You have P processors, and you have W1 tasks on the first level.
Is W1 greater or less than P?
It can be greater or less. Yeah. How much time? Let me possibly. It is a little bit of confusion. So you have W elements here, and you have P processors. What is their time they spend? It is enough to execute all W tasks.
W divided by P.
Yeah, W divided by P.
Shouldn't we round it?
Yes. That is more precise answer. Thank you, Alexander. Yeah, so we have to do like that. So we have W divided by P rounded up. Because like at the end, we could have only 2 works and everything else empty, like the processors will be idle. Okay, so then if you split level by level, you will have W1 divided by P plus W2 divided by P plus so on plus WS divided by P. Here is a little bit simple trick that everybody knows about. This is not bigger than W1 divided by P plus 1, where we go always to the upper border. So W2 P plus 1 and so on. which is at the same time, if you calculate this properly, so you have divided by p plus s. Okay, so you have here plus 1 at each level. Since the number of levels is s, then we will have s here. And here goes w, all the w's summed together and divided by p. So this is exactly what we wanted. So this is w divided by p plus s. You can get a little bit more further. The Brand's theorem works a little bit better. A little bit. But it's never written in this more complex case. You can update the calculation to that. Yeah, p minus 1 divided by p. I mean, this proof is pretty obvious, I think. What should I change? The change is pretty simple. So if we calculate a little bit more precise here, we shouldn't add 1. We should add p minus 1 divided by p. Why so? Because you go upper to the nearest integer up. If you're almost integer, like, I don't know how to properly explain this. If w1 divided by p is integer, it is never going up, right? So you never have to add this one. Then this w1 is a little bit bigger than the guy that divides by p, and then there is p minus 1 divided by p more to him.
It's like the worst case.
Yeah, it's the worst case of the level by level scheduler. Yeah, so this bound wasn't tight. This one is. Does it make sense, or it's you didn't understand something?
I just thought that if we want to calculate exact time, then we should take remainder for
Yeah.
W.
Yeah, we should. Yeah, I agree with you, but like we kind of doing this in generic case. Try to do. Okay. Then another interesting theorem is that any greedy scheduler that you have online works in the same asymptote, like works not worse than that. So right now we have this DAG that we discover. And the greedy scheduler doing the following: it finds all the tasks that are ready and execute them in batches. Kind of you have p processors. Each processor, like we have the number of ready tasks. So the tasks that are ready to be executed. So like as you remember in this DAG. In this DAG, like if I have this colored, this guy and this guy are ready to be evaluated because they have no incoming edges to them. They have no dependency. Okay, so we have like at each step, kind of our scheduler, greedy scheduler will give us some p number of operations there. So we have this magic oracle that can do everything for us. There are two cases. The first case is pretty simple, is that there are p ready vertices. But sometimes, especially at the end, you have no p, or at the start, you do not have p ready ready vertices. So you have some, I don't know, some x1 to x. The problem with that all their other processors are idle. They don't have anything to do because you have only x works ready. But the most exciting thing here is that if you have only these ready vertices, like, and they're less than p, so this means that these are the only ready vertices in the graph right now. So this x, this is kind of a look in the DAG, in the directed acyclic graph, right? And since there are no other ready vertices, these are everything we have. And when you evaluate it, the path to their end becomes shorter. So if the path here was s, then starting from here it will be s minus 1. Like, yeah, they always can create another. Yeah. That is why so there can be two cases. If we have p work p, we have p ready tasks, then we just do it and divide the work by p. But when this happens, what we are doing, let us add the number of idle tokens where the processors skip the work. Like these are idle tokens. These are ready vertices. So for each idle processor at each moment, we add idle vertex. But we know that number of such not full operations where there is some idle vertices, it always decreases the span by 1. They always decrease the length to the end. So you can have this only s times. So the total number of work that we spent is something like that. You have W, where the total number of ready vertices in the whole execution plus s times p minus 1. So if we calculate two types of tokens. So the first type of token is the work token, which you just execute, and there are idle tokens, which you do nothing. So kind of but you still pay for the operation. So this is the total number of tokens that there are, but on each operation we have p processors, so they're done in parallel. That is why you have this. So you have p processors, and the total number of tokens is this one, not more than this one. And because at each step, each processor creates at least one token, then you can divide it by p. And then in total, and for this greedy scheduler, we can get exactly the same complexity as for the Brand's theorem for the level by level scheduler. Let me check what I have to tell next. Are there any questions about this part?
By W we mean all the work, or just situations when we have exactly
we think that the token can be of two types. It is either work token or idle token, and the number of work tokens in total will be W. Okay. And this part calculates only their idle tokens. Okay, why this was quite an important issue of this theorem. Can you tell me what is the maximum number of processors that is reasonable given the work and span? You have work W and span S. What is the reasonable number of processors, like at most when? I mean, yeah, probably I again complicate it a little bit. The answer is pretty simple. It is W divided by S. Why so? Because if you have W divided by S, you will have 2S here. And you cannot get any lower than S because it isn't divided on P. So it is still S. And it almost never goes down. So there is no reason to take the number of processors more than W divided by S. I think it's kind of reasonable, I think. Because, yeah, again, I already told, this will be the main summand of this statement if we take W divided by S. Our main, then, do you understand that? This is W divided by S. There are no questions. I mean, this is not the pure answer. Like this kind of give you an intuition between. So for example, if you have work n logarithm n, and you have span n, then you don't have you cannot utilize logarithm n processors. There is no. I mean, here is not much parallelism on this algorithm. Because like n logarithm n and n, they're pretty close, and it can scale, but up to logarithm n. Later, it will be kind of like their plot will be like that. Kind of.
The main idea is that if work and span differences.
Difference large, yeah.
So the algorithm.
Yeah, exactly what I'm coming to that. Yeah. So how we will try to find the algorithms? At first, it should work well on one processor. There will be a constant overhead, multiplication overhead, but still we want the work to be as best as possible. So we want that our algorithm on one processor performs very well. So at first we optimize work. Then with the fixed work, we want to find the algorithm that has smaller span as possible. Typically in our algorithms, work will be O of work will be the polynomial of n, poly of n, and span will be of polylog of n. So this is typical our task in these algorithms, to make the polylogarithmic of n and polylogarithmic of span. Sorry. Polynomial of n and polylogarithmic of n. Polylogarithmic of n, it is the polynomial of logarithms. So typically there will be like, I don't know, like for merge sort. You know, you will have n logarithm n here and logarithm squared there. Something like that. Yeah.
Are we sure that we want to optimize the work for one core? Because probably there is some algorithms that works a bit on one core, but scales very well on 2 or 4 threads.
Yeah, we will have this discussion in 3 lectures. I mean, there is a nice way on how you have like kind of there are algorithms that works pretty parallel, but it works a little bit worse. So we kind of take our standard problem, update it a little bit to shrink its size, and then we run the worst algorithm, but much more parallel. So like we can construct from this algorithm some interesting pipeline. I mean, why we do not why we want to have optimal work is that we consider we don't think about large number of processors. We're not talking about 10,000 or so. But reasonably, the work is typically polylogarithmic. I don't know. Span can be square root of n. That would be also enough. If you have work n and the span square root of n, it's also fine, because if your n is, I don't know, 10 to the power 3, then you have all the parallelization ends on, if it is 10 to the power 6 and this is 10 to the power 3, your parallelization is until 1,000 of processors. Nobody typically have this right now. So,
but we are talking about lightweight threads, so I suppose in some applications it is possible to launch this number of lightweight threads.
No, the lightweight threads, yeah, there will be a lot of lightweight threads, but this P here is the number of processors. It is the number of cores. So, and you just, like, if you divide this work by this span, you will have like 1,000 of cores. Kind of like, yeah, it's kind of ridiculous. I mean, in the future it will not be ridiculous, but right now 1,000 is ridiculous. And that is why kind of the people trying to optimize work and then minimize span. So like it will work good in any condition. Okay. What about the time? Okay, I think I need to end, right? In 15 minutes.
Until
Okay.
8:10.
Until 10. Okay, I will not go then. Will I go? I have no idea. No, I think I will try. Like with fork join, we could ask the next time. We could talk about that. Yeah, I think that is it for today. To be honest.
Can you tell us if there is any some other resources like books or something? Like
Yeah, I will send you in the chat the book and like everything. I will send it.
And about exam and stuff, can you tell us how it's being?
Yeah, sure. Yeah, that's a very good questions. So almost each week I will give you the homework, for which I will send the instructions. You just have to solve the tasks, and I will just read them and like put some points in it. What I say is that there is a trick here, is that I will make it obvious right now. If you do something on the task, something reasonable, and you haven't achieved the right complexity or something like that, I will still give you 60% of points. So like you will get zero. Like typically you will get zero number of points if you don't do anything. Like if you did something, I kind of try to get. So for example, if there are like 3 tasks and you wrote only one thing about the first one, then you will get 1/3 result. But if you have like the first task and then reasonable ideas by the second 2, you will get like kind of 1/3 plus 2/3 times 0.6. It's a little bit more complicated here, but like so you will get instead of 1/3, like if you write reasonable thoughts, you will get this amount back. So, yeah, so this is, I mean, I don't want to make this course pretty mandatory in the sense that it's not really hard to finish. Yeah, so this is about the tasks. Also, there will be 2 homeworks that you have to implement. Something. Yeah, let me talk about this a little bit. About how to write this. So I suggest you to write it in C++. If you don't want it, you can write this on Kotlin or Java. It will still work, but from my perspective, it is a little bit more complicated. So there will be 2 tasks, which again will be measured by me, but you will defend it with me through Zoom. And we will have a Zoom session where you just come and I look through your code and give some comments, something like, and understand why have you done this or why you have done that. For C++, I would say there are several frameworks that allow you to do kind of fork join. So there is OpenMP, Intel TBB, OpenSilk, and Parallel. So nothing really happened from the last year, but like this time I added Parallel. What I could say about that, OpenMP is not very good for the nesting. So in the kind of, if you want to write the merge sort, you just have like fork join nested. So you kind of like, because merge sort is the fork, it is divide and conquer problem. Kind of you split into the half and execute everything separately. So it is ideal for the fork join. So you kind of split into the half and recursive going there. So OpenMP is very good with parallel loops, but I wouldn't suggest to use it. About OpenSilk. OpenSilk is quite a good thing, but you have 50% chance that you will not install it. So like let's delete it from here.
What this chance depends on?
I have no idea. Like I did, Ilya didn't. So there is like, this is exactly 50% of chance. Yeah. I mean, it normally, it kind of typically normally installed on the clean machine, but if you have something going on your machine like that guy possibly will not be able to install. Then there is Intel TBB. Intel TBB it has their fork and join semantics. It can do the similar thing to that, and it is included in the GCC compiler. I think right now, yeah, it should be. It should be. I mean, up to GCC 7, OpenSilk was in the compiler. Then Intel has moved to the TBB. So or even on 5. Like I was writing on Silk like in 2015s, 2018s, and it was fine because it was inside the compiler. And then they got kicked out of the Intel compiler, and they did OpenSilk on top of LLVM. Good luck, guys, with that. Because like for that, like they made it so inside the LLVM, so you have to compile GCC for LLVM, and that is why it is complicated, because you have to make compile another compiler in total. And there is a Parallel, which is the library on C++. It is quite good. These are, so I would suggest the only difference with Intel TBB is that you have to install Parallel separately. This is the code, this is from GitHub, so you have to understand how to install it properly as the library. I haven't seen, I didn't really work with Intel TBB. I worked a little bit with Parallel, and it seems to be simple to install. So there shouldn't be any problems. Yeah.
What is the problem of using native threads or something like that in C++?
Yeah.
Spawning another thread each time we want to fork and wait.
Which thread? P thread?
For example.
Okay, that's exactly the problem. That is why I was talking about lightweight threads. When you have P threads, the P thread is really heavy. It takes a lot of time to create, so you pay a lot of additional costs.
Or spend some time pre-processing, spawning all threads, making some kind of thread pool, and then using it.
Okay, but this is kind of like that. This is thread pool in some sense.
Yeah, and then just use it in our fork joins.
Okay, and what are you going to like? You have created the task. What happened with the task? You send it to the fork join pool.
No, I send it to one of the threads I created earlier. It starts.
How you do it? Manually?
Yes.
Okay. I will let you write your first homework using manual allocation of threads. Okay. So you will be given like 4 threads, and you have to get the proper scalability. Okay. Does this site looks fine for you?
Well, it's just from the point of time where I am. It is not very clear why we should use something else.
I mean, you can use fork join pool. You can like this is kind of fork join pool there. Not fork join pool. Pool. It is kind of the same. Like, let me briefly, do this. So by under that there is work stealing technique typically. So you have P threads. So you have P, and each one has its own tasks that it's going to execute. Kind of this is pool. As you can see, this is pool. Kind of you just create a new task, put into this pool, and it will be executed. But it is done implicit, so you don't have to do like in Java with fork join pool, where you just this one has to go to the pool and do it. Like it is done here through the kind of fork join semantics. And with work stealing, what's happening, if like the process has nothing to do, it just goes to the random processor and take its half of the work to him. So this is kind of pool. So this is exactly the pool where you send the tasks, and the tasks are lightweight threads. Exactly. So this is exactly what you were talking about. So I'm like, it is normal that if you write in Java or in Kotlin with fork join pool, that is fine. Because you were operating there on runnables. In fork join pool, you just have your tasks and like put it there, which is runnable, and you don't care about what else it can do. Like, and here is kind of the same. So the runnable, in some sense, is the lightweight thread in the context of Java. So like the lightweight thread, kind of the lightweight thread is the function, or the task that you are going to do, and you just the problem is that for the in comparison to the task, it is a little bit more complicated because you have to store the stack and everything else that, like the variables and everything you should carry with yourself. So this is a little bit more complicated than a task, but like still it is quite fast. Okay, let me.
So these lips just provide us.
With high level, with high level implementation of loop, Oh, sorry, not loop. Pool, So I mean, unfortunately, I would say that fork join pool in Java works well on their homework tasks, but if you want to write something on your own on very large machine, I wouldn't suggest to use Java. because fork join pull is too slow there. Yeah. It will be changed when they how they're named. Like Java created their own name for the lightweight threads, not the green threads. I forgot how. Not fibers. Looms, like Project Loom. Yeah, the Project Loom where they do this threads. Okay, so let me tell you the homework, and we will go. Like I will again repeat it in the chat. You will have 1 week to send this homework. I will accept it before the start of the class, before the start of the next class. So before 6:40 next Tuesday. Next Monday.
Should we write our solutions in LaTeX?
It's better if you write in LaTeX, but if you like make a screenshots and put it into the PDF, that would be also fine. But I have to understand what you have written. Like
Something readable.
Just something readable, yeah. So like the first task is pretty simple. So you have an array. You're given an array and you're given an element x. And you want to write an operation fill x. So you want to copy this element to all the elements in the array, and you have to do this in 3 ways. You have to do this in EREW, CREW, and CRCW. I will not tell the exact complexity, exact time for that. So there is like you have to understand what time should be for this algorithm. So not work, but time. So and please write the algorithm itself, like in this models. And the second task, please show me that like level by level scheduler from the Brandt's theorem, where we have W divided by P plus S, that it works, it is too optimal. This means that even the best scheduler you are given, it cannot be faster than 2 times the level by level scheduler. Not faster, yeah. In other ways, that the level by level scaling works no more than 2 times slower. Okay. Are there any questions in YouTube? You know, like, has someone? Oh, there is one person there. Cool. I mean, there. The thing is that I decided not to go in Russian language because the lectures are almost the same from the previous year. So we haven't finished a little bit this lecture as comparison to the previous year, but I will fit it next week. So you can look it in Russian in the videos. Like there is at the same channel as I sent you to the Telegram chat. You can just simply watch Russian videos and get over it, and then I will do here in English. Yeah.
Is this strategy of minimizing work and then minimizing span created only for fork join or for parallel models like Piram and this three-way?
Yes, of course. Yes, of course. That's kind of the problem. The problem with PRAM was that they have the fixed number of processors, so there is only one dimension really. Because you have work, which is the time multiplied by the number of processors. So it didn't really care about that. You just your way there, you had n processors. Like typically old algorithms in their papers. They're like, okay, we have the number of processors n squared, and we create the algorithm with this time. And they didn't care about work at all. So they just wanted to minimize the time, and they're like, I don't know, like if you take the number of such papers where they implement for the fixed number of threads, or something like that, they're half of the papers are on that. But they're pretty outdated, so like they're from my perspective, everything going back when the fork join was kind of not invented by fork join was accepted as the reasonable computation model for the parallel algorithms. It was done like 15 years ago. So, and before this years, like everybody was doing something really strange. I mean, there are nice algorithms. The problem is that, for example, if you have a pram, I will explain this next week, but you cannot obviously take the pram algorithm and make it to the fork join. You have to think about that, because you don't have synchronization here. You have to pay the synchronization cost right now. And because of that, typically their pram time is logarithm n times smaller than their fork join span. Still, yeah, I mean, reasonably, you have to understand also when you design an algorithm, you have to understand also the complexity, or not complexity, the constant with your algorithm. If, for example, you have I don't know, like you have the algorithm with a span logarithm n and an algorithm with the span logarithm squared, but the first one has constant 100, I don't know, like out of the blue, like you should understand that it's better to use logarithm squared algorithm. This is kind of the same as what happens with the normal algorithms, where you have like Fibonacci heap and the normal heap. I mean, Fibonacci heap runs faster as in complexity, but it has huge constant overhead. So you kind of have to also understand whether you need very complicated algorithm in comparison to pretty simple algorithm that works pretty well. So that's exactly what I was talking here. Like typically, I mean, it's easier to come up with algorithm like in squared than or.
And one more question about the run. So in our some example, we had like skip for four steps.
Yeah.
Can we skip for variable number of steps? No, I mean not variable, but depending on ID and.
Yeah, sure, exactly. Like yeah, for the pram, each processor is given its own program. So I has written it in one kind of function that has parameter ID, but they're not necessarily to have the same generic function. They could have like separate functions for each one.
How algorithms in pyramid model works in real life? Because in real life we have no such free synchronization.
Yeah, they don't work. Yeah,
Okay.
this as I was told, this thing was invented in the 70s, where nobody knows how their parallel machines will look like.
And it's just a model.
It's just a model, yeah. So like
Okay.
during this lecture, kind of I go through the old model and everything that was else, and I present you the model that we're going to work in with. Like this is the fork join model, and like possibly this is done exactly for this first task that you have to do on your homework. Okay.
Had someone tried to benchmark the pyram model?
There is in the University of Maryland, there is a very cool guy, but he's like Uzi Vyshkin. I don't know, he devoted some of his time to write their tool, or like kind of their execution tool that runs the PRAM programs on a real machine. And it seemed like, as he advertised it to me, it worked pretty well. I haven't tried it, to be honest, but he told me that it works very good. You can find it, I think, on his site in the internet, on his personal site. So yeah, he has kind of their tool that executes PRAM programs, and he teaches the students to that program. I'm a little bit more possibly modern stuff. I mean, I don't want to like say that Uzi Wishkin is doing something very strange. No, like, I mean, if someone could implement their tool that really runs the PRAM fast enough, that would be a very great thing, because like this means that someone kind of implemented the semaphore for P processors that is pretty fast. I mean, that would be groundbreaking from my perspective. Okay, are there any questions? Okay, thank you very much for coming. See you next week.